All right. Okay.
I'm taking you back upstairs, so I introduce you to the worship. I've got a meeting to go to. Yes, Satish, I know, I know. It's our fault. It's not Tracy's fault.
Was that?
They didn't have it with cookies around. But I'll get cookies. See, he's not gonna come here.
Satish said we have to start.
Well, he's mad at me. I didn't bring cookies. There's no cookies for Satish.
Just come for the cookies. Just come for the cookies. No, I'll stay here for this.
He's gonna get it, they'll pay everything away. No, it's locked, so yeah, I'm gonna go take the key away and. So next week. Who's running a remote version? I invited a whole bunch of people from PCA yesterday.
Oh.
Good show. Are you running the, are you running the remote thing? No.
It's a camera that's recording, and I think we're online.
We'll wait another minute for Jamie to come back. Okay, well, I guess we'll go ahead and get started. For those of you that don't know me, I think I know a few of you here. Joe Magner, Harvard Bioproducts and Biosystems Engineering. I think some of you maybe know that John Lieber is on sabbatical, and so I'm your new Director of Graduate Studies. I don't know for how long. John may decide not to come back, but we'll see how that all goes. And today we have our special speaker has come all the way from India, Dr. Srinivas. He is a postdoc, and the work that he's going to talk about basically originated from conversations with the Board of Water and Soil Resources, particularly looking at this dynamic of different tools and models that are out there, and really what's the best tool? What's the tool that folks should be using? Because at the local level, there's been a lot of angst and consternation about, well, we hear this company is promoting this tool, and this company is promoting that tool. And even at the state agency level, there's been sort of these pet projects or pet models and tools. And what we really try to do here is take a look at all these tools and provide a third-party independent review of what's going on. So with that, I'll let Dr. Srinivas explain the work.
Thank you, Joe. So hi, everyone. So since January, basically, I've been given this task of comparing these three popular tools, that is ACPR, PTMR, and HSPF SAM. So through this work, what we are trying to do is to compare these three watershed tools in order to develop a decision support framework so that we can implement decisions at a field scale level. So this work, along with me, Matt Drevich and obviously Joe Magner, so all three of us are combinedly doing this work. Matt Drevich is from Minnesota Board of Water and Soil Resources. So when we talk of a watershed planning tool, so if we want to categorize the objectives of a watershed planning tool broadly, the first piece that comes into picture is the agronomic goals. So whether it is related to the good crop productivity, efficient nutrient management, efficient water management in the agricultural watersheds. So there are many agronomic goals that are associated, which is the first thing that has to be satisfied or that has to be taken care of properly with a watershed planning tool. The second piece is the hydrology. The hydrology has to be dealt properly, whether it is subsurface hydrology or the overland flow, the movement of the pollutants, etc. So that has to be taken care of very properly. So this is the another objective of a watershed planning tool. And the third aspect, which is the most important aspect, is the social and the economic aspect. When I talk about the socio aspect, that mainly deals with the, you can say, the preferences of the landowners, because ultimately, although the planning we may do at a watershed scale, but the implementation has to be done at the field scale. So this involves conversation with the various agencies and the landowners so as to ensure that the implementation strategies which we are proposing, they are implemented at a field scale level. And then comes the economic piece, which is the most important aspect, money. So although we want our nutrient reduction goals, the pollutant reduction goals, sediment reduction goals to be achieved, but ultimately it has to be achieved with the available budget. So we have to come up with an optimized solution to satisfy all these three goals in order to have a sustainable decision support framework. When I talk of sustainability, we mean that it should fulfill the needs of the future generation as well as the present generation. So such kind of decision support system, it should be able to achieve the following things. The first thing is the hydro conditioning. So in very short, hydro conditioning is, although we have a high resolution LiDAR digital elevation model, but still it is not sufficient to, to represent the stream network properly. So hydro conditioning is the first thing that has to be done properly in order to represent the hydrological pathways accurately. Then the decision support system, it should be able to give the targeted sites for the placement of various pest management practices or the conservation practices. Then once you have these targeted sites for the BMPs and the CPs, then we have to see are they able to achieve the nutrient reduction goals, or to what degree they are achieving the nutrient reduction goals or the sediment reduction goals. Obviously, as I talked about cost, these all practices should be cost effective. They should be able to satisfy the budget that is available with the state. Then it should be able to incorporate the landowner preferences before delineating any of the targeted site for the various BMPs and the CPs. And once you have all these things done, the last aspect is that it should be able to develop optimized scenarios, and it should be able to have the TMDLs that are required. When I talk about the optimized scenarios, primarily we are talking about achieving the load reduction with the available budget that we have. So now the question comes, can a single tool achieve all these things? So we have many tools. We have water quality analysis and simulation program. We have basins, we have HSPF, we have SWOT, and now these three latest tools which have come up. So can a single tool achieve all these things? So this is the purpose of this study. We try to see that how these three tools, that is ACPF, HSPF, SAM, and PTMF, are able to reach these goals to different degrees. So the study begins with comparing ACPF, PTMF, and HSPF, SAM. So what are they? I'm going to discuss in the coming slides. So it begins with comparing these three tools, identifying their strengths and weaknesses, and try to utilize their strengths so as to develop this decision support framework. And then using a proper combination of these tools or either one of them, we try to have a targeted practices so that we can implement them at a field scale level. And finally, with that, we develop a decision support framework so that we can empower the local watershed users to implement the practices which we have given so as to achieve the goals. So the tools which we have worked upon in the last 9 to 10 months, the first thing is ACPF, that is Agriculture Conservation Planning Framework. So this has been developed by United States Department of Agriculture and RCS, and mainly it deals with the planning at a HUC 12 level. And the maps which are produced by the ACPF are very useful to do the field scale analysis. The primary focus of this tool is soil health, the erosion, and the 4R practices. And some of the main highlights of this tool, it deals with the tile drainage analysis very well. It performs terrain analysis very well, and it focuses a lot on the riparian assessment. The next tool is the PTM app. It is prioritize, target, and measure. So as the name itself suggests, so it tries to prioritize the most polluted sites in the watershed and tries to measure the extent of pollution, and then it comes up with the targeted practices. So this has been developed by Board of Water and Soil Resources, Bowser, and the Houston Engineering. This can be implemented at a HUC 8, HUC 10, or HUC 12 level. Although ideally when it was made, the software, the main intention is to move ahead towards one watershed, one plan, that is a HUC 8 or a HUC 10, although it is implementable at a HUC 12 also. So one of the main focuses of this tool, yeah.
What is a
Okay, so it is a hydrologic unit code. So when we talk about watershed planning in a very simple language, we do it at different scales. If we talk about HUC 12, that means we are dealing about 30 to 40,000 acres, a total area, and we are doing planning in that. If you talk about HUC 10, it is about 1 lakh acres. Then you talk of HUC 8, further more area. So that's how, in a very simple language. So then the primary focus of PTM app is to have water quality benefit and cost analysis. So when I talk of water quality benefit, it mainly talks about what are the nutrient and sediment reduction goals that can be achieved, to what degree it can be achieved by the various practices. And then what is the cost associated with it. And then PTM app, it also gives what is the effect of using the various practices in combination with each other or in series. Then comes the HSPF SAM. It is HSPF Scenario Application Manager. So it is basically based upon the HSPF model, which is being run in almost all over the Minnesota Hydrological Simulation Program Fortran. So it is a very robust and calibrated model, and it is being developed by Respect Consultancy and MPCA, Minnesota Pollution Control Agency, together. Ideally, HSPF was built to have watershed plan at a HUC 8 level, although it can be applied for a HUC 10 and HUC 12 as well, but this is initially it was conceived for HUC 8. It is based upon calibrated HSPF model. One of the main focuses of HSPF is to design various scenarios to achieve total maximum daily loads. So this is something which these other two tools are not doing, but HSPF does very well. It deals with the cost analysis. And finally, it optimizes the water quality improvements. So what basically I have done, I have tried to apply the best way to compare these three tools is to apply it in a particular watershed and study their outcomes and try to compare their results, so as to understand what is the dynamics that is taking place behind the tool. So So Huckwell Plum Creek watershed in the Cottonwood County. So this has been taken as a study area, which is Huckwell, and the total area of this is about 30,000 acres. And the Plum Creek, the total length is about 35 miles. So this is the crop data layer for the Plum Creek watershed. So now I've tried to use all these three tools or develop models on the Plum Creek watershed by using these three tools. The primary data which have been used is high resolution LiDAR DEM digital elevation model, then the land use data, soil survey geographic database, then comes the Russell inputs, that is revised universal soil loss equation inputs. Then comes the crop data layers, the HSPF model outcomes, sediment and nutrient time series data, and finally the National Hydrology data set. The primary sources are Minnesota Department of Natural Resources, MPCA, USCPA. So these are the primary sources from which the data has been collected. So now as I talk, the first aspect which these three tools should deal with is the hydro conditioning. So before using any of these three tools, so what I have done, we have taken the original LiDAR derived DEM and performed the hydro conditioning. I know most of you, at least the students, you may not be aware of the hydro conditioning, but in a very simple language, when you have a LiDAR derived DEM with you, so if in your DEM there are some roads or there are some culverts, then your flow gets impeded. So this is the depth raster that is being derived from using GS. The flow gets impeded, and because of which the flow pathways are not effectively represented, or the flow network is not effectively represented by the DEM. So these pathways have to be represented in an accurate way. So hydro conditioning helps in doing that. It begins with first removing all the false depressions that are there in the DEM. Then it identifies all the impeded flows. It simulates accurate flow network. How it does it? It simply does it by placing various dam and cut lines. So it identifies these locations where there is impeded flow, and then manually we can connect the flow, we can develop the flow network across these impeded flows. So there are various levels of hydro conditioning that are being used, but since we are talking about a field scale modeling, so the hydro conditioning which is being performed in this study is H3DEM, which is a very good level, although the highest level is H3DEM plus, but H3DEM is also helps fairly well in field scale implementation. So now if you see this is a more enlarged image. This was the condition before hydro conditioning was performed. And now once the hydro conditioning has been performed, all those impeded flows are removed, and now you have a complete flow network. There are no backed up flows after hydro conditioning. So I'll directly switch gears to the outcomes of these various tools. I'll not discuss about how these tools work. I mean, that takes a very long time. You can contact me separately for that, but we'll mainly focus upon the outcomes. So it begins with ACPF, Agriculture Conservation Planning Framework. It first begins with dividing the entire watershed, the HUC12, which is being used into various catchments, and it identifies the watershed outlets or the pour points. One of the ACPF things which ACPF does very well, it delineates the entire stream network. This is your main stream, or you can say the perennial stream, and then there is the entire stream network which is being delineated. Then, obviously, our main concern is what is the extent of erosion that is being taking place throughout the watershed towards the various streams. So ACPF, it helps to analyze what is the distance of the various locations from the stream. You can see the blue color, it represents a very low distance in meters, and the red represents very high distance. And then this analysis is being used to carry out the runoff risk assessment. Then it identifies which areas are more prone or very highly prone to runoff and which areas are lowly prone to the runoff. Then, based upon the runoff risk assessment, ACPF also calculates further more parameters, like it calculates the stream power index, it calculates the topographic wet index, and then it gives us the locations of the various management practices, like where to have grassed waterways or contour buffer strips. So these are the various locations where you can have grassed waterways or contour buffer strips. These are the locations which are tile drained. Based on that data, ACPF gives where are the locations where you can have drainage management practices and where you can have bioreactors, where you can have nutrient removal wetlands. And this is the more closer view of that, the bioreactors and the nuclear removal wetlands. One of the advantage of this tool is it not just gives you the locations where you should have bioreactors or nutrient removal wetland or any of the practices, but it will also give what is the area that those practices are going to occupy, what are the dimensions of those practices. Then comes the water and sediment control basins. The farm ponds. Then one of the exclusive feature of ACPF is it digs very deep into the riparian assessment. It first identifies the riparian catchments, and then it will give you the locations where you can have saturated buffers, and then you can have various kinds of riparian functions, whether it be deep-rooted vegetation or it is multi-species buffers, stiff stem grasses, stream bank stabilization, etc. And these two figures, they give the complete analysis which is being performed by ACPF. These two figures, they represent all the various practices that have been delineated by ACPF. So now, from these maps, we can generate a field scale map, and those field scale map can be taken up to a farmer or a landowner, and then comes the implementation. So this is how ACPF works. If we talk about PTA map outcomes, the first step of what PTA map does, it does the complete source assessment. So this step helps you to identify which of the locations in the watershed are contributing more nutrients or are contributing more sediments. So this is, as you can see, the legend, it gives you which are the locations that contributes more to more sediment and which are the locations contributes less. Similarly, you can also produce this kind of a map for total nitrogen or the total phosphorus. So based on this, you can prioritize the various locations. You can know, yes, these are the locations where you have maximum loading coming, and yes, I need to have some practices here. So this is the first step of the ACPF. Then once you identify the various priority resources, then it gives you the locations of the various practices, whether it is infiltration, biofiltration, filtration, protection, storage reduction, or source reduction or storage. I'll explain them when I come to the further slides. These are the locations where you can have various practices all throughout the watershed. So once you have all the practices, the first thing PTA map does, it first evaluates whether it is possible to have these practices at those locations or not. So this feasibility is being done based upon the topographic and the land use characteristics, or you can say the typical size of the drainage area or the land slope. So this is mainly done based upon the NRCS Field Official Technical Guide. So once you have done the feasibility analysis, then obviously a watershed planner is interested to know what are the water quality benefits that could be achieved by these various practices. I mean, what is the treatment cost? For example, for nitrogen, if you use filtration, what is the treatment cost for these practices? If you use protection to reduce the phosphorus, what is the treatment cost? So this gives helps you to analyze what is the total cost that is going to take place if you are using a particular management practice for a particular pollutant or sediment. So now once you know what are the water quality benefits, then comes the most important piece, that is the cost. So then PTMAP, it runs the cost effective analysis and it just gives you the location of the cost effective practices throughout the watershed. For example, what is the cost effectiveness to reduce the sediment lesser than $10,000 per ton or total phosphorus? So now you can see before PTMAP has delineated so many locations that were more than 1,000. But once you have this constraint on the cost, it gives only 133 cost-effective practices, which are primarily composed of storage and protection. So this is the whole way the PTMAP works. As you can see, the ACPF, it has also given the locations of the management practices. PTMAP has also given the locations of the management practices. So this is just a table which shows what are the various pollutants, what is the cost associated with the various BMPs, and what is the total sediment, phosphorus, or the nitrogen that is going into the various BMPs, and what is the associated cost. So now coming to comparing the outcomes of ACPF and PTMAP. So now PTMAP, it mainly categorizes all the practices into storage, filtration, then biofiltration, infiltration, protection, and the source reduction. So now each of these practices can be further categorized into, for example, storage can be categorized into vast scopes, drainage management, farm ponds, nutrient removal, wetlands. Similarly, each of these practices have certain functions. So the ACPF gives a very precise location of all these practices. And as PTMAP gives the precise location of these practices, so we have tried to have a comparison between both. So if you see for the bioreactor, these are the locations which are, the red dot shows the bioreactor locations which are given by PTMAP, and the green one shows for the ACPF. As you can see, there is, although PTMAP and ACPF, the results are matching to some extent, but ACPF gives far more locations for the bioreactor as compared to PTMAP. And if you talk about contour buffer strips and the grassed waterways, PTMAP gives a far more locations than the ACPF as far as the grassed waterways are concerned. Then if you talk about protection and the storage, PTMAP gives, for the protection, PTMAP gives locations almost at a lot of locations in the watershed. However, if you see for the ACPF, it not only gives you water where you have to have protection practices, but also gives you what kind of protection practices that you should have, whether it is deep-rooted vegetation, multi-species buffer, stiff-stem grasses, etc. Similarly, storage, which includes vast scopes, farm ponds, etc. ACPF gives the various locations, and then PTMAP gives the pink dots, it shows the PTMAP. So this is one component storage where PTMAP and ACPF results are matching to very good extent, that is more than 70%. So this comparison which has been done, that was done at an initial stage where PTMAP has not done any cost analysis. Once the cost analysis is done, then the results of both ACPF and PTMAP are matching to more than 70%. So these are the various locations of PTMAP and ACPF. If you want, PTMAP are represented by this orange and the pink color, which are mainly storage and protection. As we saw, it delineates total 133 practices. And then all other locations are given by ACPF. The number of sites which are being delineated by PTMAP are comparatively more than the ACPF. I'll focus upon why is this happening. Primarily, the difference is coming because ACPF, it mainly focuses upon tile drainage, terrain analysis, the stream network, and the riparian assessment. PTMAP mainly focuses upon the cost analysis and the nutrient loadings. So ACPF, it doesn't deal with nutrient loadings and cost analysis at all. if you see contour buffer strips, around 70% of the ACPF sites are the subsets of the PTM map. These are the contour buffer strips, which are represented by purple color. Similarly, the bioreactors, both tools are matching to the good extent. Nutrient removal wetlands, this is one thing which ACPF performs which ACPF delineates very well because it deals with the tile drainage very well. So based upon these outcomes, we have drawn some conclusions or some comparisons of both of these tools. If you talk about nutrient sediment loading and source reduction, PTM app does it based upon the Russell inputs and sediment delivery ratio. ACPF doesn't take care of this aspect. If you talk about tile drainage, PTM app does deal with that, but ACPF digs deeper into the tile drainage based upon the soil and the slope conditions. Terrain analysis, again, ACPF, it finds the stream power index, topographic wet index. It used D infinity method. So it does deal with terrain analysis very well. Then comes the runoff risk assessment. PTM app does that by using Russell inputs. ACPF does it, as I discussed, by using the slope steepness, distance from the stream, and identifying the perennial stream network. Coming to runoff volume and peak flow, PTM app does calculate these factors, but ACPF doesn't. Now, when you try to talk about implementation on the field scale level, ACPF does it very well as it can generate field scale maps. One of the reasons why it does very well is because it distinguishes between agricultural fields, pastures, lands, and forests. It primarily focuses upon the agricultural field only instead of entire watershed. Coming to feasibility analysis, PTM app does it based upon size, cost, topography, etc. ACPF primarily does it based on size and topography, doesn't deal with cost. Why ACPF generates field scale maps very well? Because it has an area threshold of 15 acres, which can be further modified so that stream network can be represented properly. However, PTM app, it has an area threshold of 40 acres. PTM app doesn't generate the pore points, but ACPF does. Then comes delineating stream network. ACPF, it delineates the stream network by dividing the streams into perennial streams, ephemeral streams, etc., and visualizes flow paths for every 5 acres. And it develops flow network very well. Then comes the riparian assessment. PTM app delineates the locations for the saturated buffers. However, ACPF, it goes further deeper into the riparian assessment. So now, if you talk about the strong aspects of both of these tools, I mean, if you want to conclude what are the strengths of these tools, PTM app, the main strength is nutrient and pollutant loading and cost benefit analysis, and the ACPF, the main strength is terrain analysis, tile drainage, stream network development, and the riparian assessment. So now what I've tried to do, I've tried to utilize these various strengths of these two tools and try to ingest ACPF results into PTM app so that what aspects ACPF doesn't do, that can be done by PTM app. That is the nutrient loading and cost benefit analysis. And this way we can have a more accurate delineation of BMPs and the conservation practices and the field scale maps. So once we have done that, these are the various locations. The total number of practices, which were earlier 133, now it becomes 537. And now all the ACPF polygons, they consider the nutrient and the pollutant loading. It estimates water quality benefits. And now we also have what is the constituent delivery to each of these practices. So this is the table that gives the information about what I have talked just now. And the final thing is the HSPF SAM outcomes. So one of the exclusive feature of HSPF SAM as compared to other two tools, it finds what is the impact on the reach. It finds what is the impact on the streams. So it finds reach load, reach concentration. So this is something that the other two tools, they don't deal that well. For example, what is the total phosphorus reach concentration? So this is being represented by this figure. These are the various reaches. And then this is the reach and the source load in a graphical way. So this is the average total nitrogen. When I talk about average total nitrogen for base, that means for a base condition. I mean, no scenarios have been developed. It is just simply utilizing the HSPF model outcomes. And this is the nitrogen, and this is total nitrogen source load. That is the nitrogen being contributed by the various sources. And then you can develop various scenarios. For example, if you want to replace a developed land with a grassland, what is the cost and how much area has to be used? So this is what HSPF does very well. For example, I've developed a scenario where 20% of cropland high tillage area has been replaced by the grassland, or 20% of developed land to the grassland. And then it gives you the entire 24 options of the various management practices. So this is a flexible nature of SAM, which allows the watershed planner to choose the various practices. So the practices which are being delineated by ingesting ACPF into PTMAP, we have used only those practices we have ingested into HSPF SAM, so as to see what are the outcomes of the SAM. So one of the exclusive feature of SAM is it also takes care of the participation level of the landowners into picture. It gives the degree of acceptability of the various practices by the landowners. However, SAM, it doesn't give you what is the exact location of the various practices. Therefore, what practices to choose, it needs expertise about the watershed characteristics. For example, if you want to have riparian buffer, so this is the treated area, this is the total cost, this is the percentage suitability, total cost, and these are the various sub-watersheds within the watershed that we have chosen. So these results fairly match with that of ACPF and PTMAP. As I said, SAM gives the percent suitability, it doesn't give the targeted location. So this is the percentage suitability, this is the total cost. So I've tried to develop two scenarios. Scenario one, we have added all the management practices which are being derived by ACPF and PTMAP, and scenario two, along with these management practices, we have made some climatic changes. So this is how we develop various scenarios. So we added all the practices, and there we have chosen a severe climate scenario just to see that what would be the impact, what would be the pollutant loadings, what would be the impact on the reach if climatic scenarios, climate becomes severe. So SAM really helps in comparing the various scenarios. It helps to understand what are the load reductions that are being achieved by these scenarios. It helps to understand what is the cost associated with these scenarios. This is really important to have any kind of decision making. So for each sub-watershed, for example, for A191, this is one of the sub-watershed. Total phosphorus, what is the total phosphorus that is being achieved by each of these scenarios? This is phosphorus with respect to dry flow or the low flow. And then what is the percentage reduction of total nitrogen per dollar invested? So this is again, this analysis is being done by SAM. So then you try to develop a scenario with a total maximum daily load of 0.1 mg per liter. So I'll just quickly go through it. So this is the percentage reduction that is being needed from the current load to the TMDL that we have set, that is 0.1 mg per liter. This is what is required, and this is what is being achieved by scenario one. So now this data, it really gives a lot of clarity to the decision maker that to what management practices we should have, and if we have it, then to what degree they are achieving the TMDLs. And now let's say that you want to find out what is the total cost that is associated with the 15% reduction of the total nitrogen. So SAM, it will use all the BMPs that you have chosen, and it will tell you this is the total cost that is associated with it. However, if that much cost, that much budget is not there, and let's say you fix the budget, then Sam will also tell you that if you fix the budget to this much, then to what degree you are going to achieve your target. For example, you wanted to achieve 15% reduction, but if you fix the budget, you are going to achieve only 8.5% reduction. And in this process, Sam will automatically filter out all those management practices which are low ranked, and it will have only best management practices on the field. So if you compare these three tools together, HSPF SAM, since it is based upon HSPF, it's a calibrated model, and PTMAP, it is based upon the Russell. However, the best way to understand the accuracy of ACPF is to have interaction with the landowners. All three tools can use hydro conditioning. SAM offers a wide range of BMPs and helps in developing TMDL scenarios. It deals with point and non-point sources simultaneously. But as I said, SAM doesn't give you the ideal location, targeted location of the practices. Therefore, it needs expertise to apply SAM. SAM deals with subsurface hydrology very well, and it helps in developing the relationship of the pollutants with the stream flow. Then comes riparian buffers, filter strips, vast scopes, SAM results which give 30% suitability. They fairly match with that of ACPF and PTMAP. Bioreactors, they also show good agreement with PTMAP and ACPF. Another advantage of SAM over the other two tools is that it considers a wide range of parameters. I mean, not just total phosphorus and the total nitrogen, it considers orthophosphates and nitrates and the nitrites. It incorporates climatic piece into the tool. And finally, the SAM strikes a balance between the nutrient load reductions and the budget constraints that are there, so as to give an optimized BMP list. It includes the opinions of the various farmers or the state agencies, the landowner preferences. Overall, it gives you a flexible environment to a watershed planner so as to develop a tailor-made scenarios in order to achieve the nutrient reduction goals. So now we have seen all these three tools, and each of these tools have certain best aspects. So remember, we started our talk with this question: can a single tool achieve everything? So the answer is, at present, we don't have a single tool which can achieve everything, but yes, we can have an integrated setup with which we can achieve all our watershed goals. If we talk about these three tools, the best aspect of these three tools, if they can combine together, then we can have, like it is being done in this study, then we can have an optimized delineation of BMPs and the conservation practices, and we can develop the field scale maps so as to implement it. That's it. Thank you. Any questions?
I'm still puzzling over PTMF versus HSPF SAM. Since HSPF SAM has the loaded cost estimates incorporated into its optimization, what does PTMF do better than HSPF SAM?
The main thing what PTMAP does better than HSPF SAM is it gives you the locations. HSPF SAM doesn't give you the locations of the targeted practices.
It just puts it within the it locates the practices within a sub-watershed.
Yes, but it will not give you a pinpoint location. So that is the main difference between PTMAP and HSPF SAM. HSPF SAM, it deals with the loadings, deals with the cost. PTMAP also does both of these things. But HSPF SAM doesn't tell you where you should have practice. It will tell you, yes, in this sub-watershed, the percentage suitability to have this practice is this much, but where to have this practice, it will not tell you that.
And how small of a sub-watershed is it targeting to?
I think if you talk about in my Plum Creek watershed, it's about maybe 3,000 acres, yes.
so much, I mean, it's a pretty small catchment, it's much smaller.
It is smaller, yes, it is smaller. But if you talk about field scale implementation, then it's not enough.
And PTMS will give you the location of the practices, but not like the dimensions of the practices, right?
Yes, it doesn't give you the dimensions which ACPF does very well. And another thing is that since PTM app, it has a lot of focus on the pollutant loading. So if you see the maps of PTM app, you will see very scattered map. I mean, if you see for grassed waterways, PTM app will just give you the locations in binary terms. It will tell you whether you can have it or whether you cannot have it. I mean, it will allocate a number 1 or 0, and it will give it throughout the. If you talk about grassed waterways, it will just take care of the pollutant loadings. But when ACPF comes into picture, it deals with terrain analysis, it deals with stream network analysis much better than PTMF. Hence, the ACPF, the locations are much more focused than PTMF. Although they are the subsets of what PTMF is giving, but when you talk about planning, you need a more focused subset. So that is why ACPF helps better in that.
I think you wore them out. You're breaking through a fire hose a little bit, you realize that, but a lot of information.
I apologize if I understand these terms are very new I could see from your faces. So, but I think this is for you people for whom these things are very new, but these things were very new for me when I came here in the month of January. So it took me only 8 months to understand these things. So, I mean, if you dig a little bit into it and study, I think you should be able to understand it even much better than me, because you are the product of University of Minnesota. So it doesn't take much time to understand these tools.
Okay, well, I think there's no, any last question, comments? Now let's give one more last round of applause. So you make it to the Water Resources Conference next week. And what a date, 3rd of St. Paul. So go ahead and
Stop the recording.
stop.